Hey everybody. In this video, I'm going to talk to you about integer data movement and pointers in an x86-64 YASM assembly program within Ubuntu, but this should work for all of you x86 YASM people. Okay, so what am I talking about for starters? I'm just talking about moving data pretty much. If you are an expert at moving data from one integer register to another, or from one general purpose register to another, and if you know how to manipulate pointers in assembly and all that stuff, you probably don't need this video. But if you are not an expert, then this will probably help you. Let me start off by saying, of course, that there are going to be lots of concepts in this video that I don't actually explain because I've explained them in other videos. For example, this is not a Hello World tutorial where I show you how to actually, build a basic YASM assembly program. You can probably infer that just from this video, but I'm not going to explain it. Also, this is not a debugging video, so I'm not really going to explain too much about GDB, which is something I'm going to use to look at the registers, but it might be nice for you to get a little preview. I will record a full GDB tutorial in another video. Anyway, so let's see here. For starters, I've just kind of like created a little sample program here. Well, it's empty at the moment, but I've created a Makefile, which will just compile and execute my program. Again, this is not a Makefile video tutorial. Check my other videos for that. I've already made one. For now, I'm just going to start making a program, and I'm going to give it a data section. So first thing I'm going to give it is like, well, let's say I'll give it a bunch of data, then I'll kind of explain what I gave it. Again, this is not a basics YASM tutorial, so see my other videos, but just simply put, I'm going to write to standard output. So I remember the system call code for writing, and then I'm going to exit because this is a pure assembly program that I'm compiling. This is not a hybrid program. We're not doing GCC, we're just doing LD. So I'm just going to say call code 60 to exit, a file descriptor for std in. Actually, I don't really need that. Let me just double check that I don't need that in my solution. Yeah, I like to reuse these things, so we don't really need standard input. We're just going to do standard output, printing to the terminal. We're going to exit with a success code of 0. And then I made a couple of, just one C string where I'm just basically saying, hello, my name is so-and-so, so you can know that the program actually started in case it crashes later. That's not my name. I just love those kinds of names. And then I'm just going to make a bunch of integers of different data sizes. So this is kind of important. In other videos, I've talked about data sizes, but just real fast, because these are going to be directly used in our video. We have a quad word here, so I'm defining an integer called mylongint, and I'm saying that it's a quad word with DQ, Q for quad word, and then I'm just giving a pretty big integer. Same thing for a regular D word, which is just a double word, so that's half of a quad word. And then another thing with a, whoops, have a typo there. That was supposed to be a W, not a Q. Let me just fix that in my solution. Oh dear. Then I'm going to do a word, which is 62111. A word is 2 bytes of data. We're starting to get dangerously into overflow territory. When I was originally writing this solution, I had like a bunch of 9s up here, and the number that I ended up seeing on the screen was totally different, and I forgot, oh, a word is just 2 bytes. So even if it's unsigned, the highest thing that it can actually represent is 65535. So that's not good. Then I'm going to just store a byte here with db and put some 2s there. And then I'm going to make an array of integers. Making an array in the regular data section, that's not as good as putting it in the BSS section if you want a lot of integers. But I'm just going to specify a small number of integers, so I can just put it directly into the data section. BSS is for like giant arrays of uninitialized data, and the data section is for whatever you can handle typing, pretty much, of initialized data. So now I'm going to start my text section and my program's entry point. Again, this is not a YASM basics tutorial. See my other videos. And so we're going to start by just saying, here's my entry point where the operating system can sort of jump into my program. And at the very end, I'm going to just, exit the program. Let's actually see if that works so far. It should do nothing, but at least exit with success. I'm going to go clear and make run. And notice how it just kind of like ran it and then nothing happened. Okay, so that's great. How come it didn't print though? Well, what did I do wrong? Oh, I forgot to copy paste the code that prints something. Okay. Let me get my solution up here. So the first thing we're really going to do is just use a system call to print the word hello. Again, this is not a system call video. See my other videos. And so now we're just going to print our hello string with a system call. Let me run it one more time. We should see like a quick hello. Yeah, okay, my name is Chaplain Mondover. It's not. Maybe I should change that to it's not. My name is not. No, I don't want to do that. Sometimes I like to pretend that my name is Chaplain Mondover. You should too. It's fun. Anyway, so the first thing that I'm going to do here is I'm going to move an immediate... Well, let me copy paste a whole chunk of code and then I'll explain it one by one. I'm basically going to use data movement instructions to move a bunch of data into a bunch of registers, and then I'm going to hit a breakpoint, or I'm gonna sort of do like a non-operation piece of code so that I can easily break on it in my debugger. So we can just kind of inspect the results. Okay, so first off, I'm gonna move an immediate into R12. The instruction for moving data into general purpose registers or the integer registers is just MOV. So that's fine. Probably you should know that by now. But I'm gonna move an immediate into R10, and I'm gonna move 12876 into R10. So that's how you move an immediate, no problem. Then I'm going to first clear out R11, and then I'm going to move R10 into it. The reason I'm clearing out R11 first is just to prove to you that we are actually moving data from one register into another. Because if I just, I don't know, if I didn't do that, you might be tempted to think, well, maybe R11 already had that data in it. So first it's going to be just a 0, and then it's going to actually be whatever R10 had. So we should see R10 and 11 both have 12876. So now you know how to move an integer register or a pointer register from one to another. And by the way, integers, those are pointers, or rather, should I say, pointers are integers. So if you're moving an integer or you're moving a pointer, the system just kind of sees that as a number either way. So you can use the move instruction for it. So now let's use the pointer that was assigned to our long integer to move that number into R12. So let me just go up real fast. My long int up here, it's like a gigantic number. And remember I said before that my long int is actually just a pointer to the memory location that begins to hold the quad word. So my long int is really a pointer to 1 byte. And there's an 8-byte allocation because it's a quad word. So when you sort of put this into your code, and you let the system know that you want to move a quad word from that memory location, then the system will scan 8 bytes and interpret that as an integer. So putting the keyword quad word here, I don't think that's necessary. I usually do it anyway, but you'll see in the next few instructions that it's a really, really good idea to specify the data size, because if you don't, you're going to actually get something wrong. In other words, if for some reason I moved, I don't know, a word's worth of data from that memory location into R12, I could do it if I wrote it correctly, but then I would be taking part of a quad word and trying to interpret that as the entire number, and it's probably going to be totally wrong. We'll have an example for that in a moment. But anyway, so that's how we move a quad word. We just specify qword right before the memory location, and we use the brackets to dereference. If we didn't dereference, then we would actually be moving a pointer to the long integer into R12. We'll do that soon too. I'm going to try to do everything in this video. Then we'll move a dword from memory into R13. This is a little bit different. Notice how here on line 60, I kind of have to specify dword because that's the data size that I'm trying to move into the R13 register. So this is telling the system that there's about 4 bytes that I need to scan, not 8 bytes, and interpret those 4 bytes as an integer. But then moving it into R13, you know, I could have sworn a long time ago you could just move that sort of thing directly into R13, but when I tried my solution before recording this video, I kept getting assembler errors until I added the D at the end. And so I just want you to know, oh, you know what, let's look at a book real fast. Let's look at my favorite book. I just want you to know that there are other forms of every register that can specify the register's data size. What do I mean by that? If you just specify R13 by itself, then the system thinks you're talking about all 64 bits of the 13 register, the R13 register. But if you type, whoops, if you type R13D, then the system thinks you're only talking about the lowest 32 bits of that register. So you're also able to specify the data size of a register. Again, I thought you should have, a long time ago, I thought I remembered moving a dword directly into R13 and it would just clear out the extra bits. But I got warnings this time. Maybe that's for the best, forcing us to be more precise, but this will solve it. R13 just says, let's only talk about a dword. So let me go to my favorite book here. Where the heck is my favorite book? Okay. I guess I have to like, there we go. Okay. There's my favorite book. So I'm going to go to, let me just search for, I can't remember where it is, R13D. Yeah, there it is. Okay, so what we're looking for is 2.3.1.1. Let me show you real fast the top of the book, just to give a shout out to the person who wrote this book. I did not write this book. This is a free and open source book that you can download for free. Everybody should get a copy to turn yourselves into an expert. It's called x86-64 Assembly Language Programming with Ubuntu. It's written by a brilliant professor. This is like a semi-recent version. There's probably a newer one now, but yeah, it's a great book. I love it. So I'm going to go back to, what the heck was I just doing? Was it 2.3.1.1? Yeah, okay. So in this book, section 2.3.1.1, the section entitled General Purpose Registers, notice how there are a bunch of different versions of each register. So if you look in this column right here, we have, oh, I get to use my annotator. We have, what were we just looking at? R12. Notice how R12 here is it designated as a 64-bit register. But if you wanted to use the R12 register and only use 32 bits of it, the lowest 32 bits, then this is the form you would use for the R12 register. So 32 bits. And if you wanted to use only a word's worth, 16 bits, well, there you go. A word is just, 2 bytes on these systems, or 16 bits. And then if you just wanted to use 1 byte of the register, well, you can. You just put a B at the end of it. It's pretty sweet and convenient. It's not too hard to remember that D is for dword and W is for word and B is for byte. It just gets a little confusing when you're using the other registers, like the RAX register. It's got EAX as its 32-bit version, and then AX as its 16-bit version, and AL as its 8-bit version. If you can remember that there's an L, I guess, that's not too bad, but remembering the X, and then it changes to an I over here and a P over here. I'm personally not a fan. So I always come back to this book to try and remember what I'm supposed to be putting for these registers, because I can't remember all the time. Or rather, I can almost never remember, but we won't talk about that. Anyway, so I want to take a dword from memory and load it up into the R13 register. So I got to specify the R13D. And, maybe I'll take that out and show you that it doesn't compile later, if I can remember. But I'm going to now take a dword, do the same thing into R13. Oh, sorry, no. I'm going to take a regular word and do the same thing basically into R14, but it's just going to be a word instead of a dword. And then I'm going to take a single byte and load it up into R15. Then I'm going to call nope, which is an instruction that just does nothing. And it's useful sometimes if you want to have a place where you can stop your program and sort of inspect the results of your program in your debugger. So there's a lot more to this program. I'm going to go ahead and just run it right now, just to make sure that it compiles. And then maybe I'll add a breakpoint here. Let's go clear and make run. Okay, so it ran, it compiled, it was fine. And now I'm going to open up a new little window, and I'm going to launch the program. Notice how the program that has been compiled is called main. So I'm going to launch the program into the GDB debugger. This is not a GDB video, so I'm going to be skimming over this. Check future videos for a full GDB tutorial. So I'm going to do a breakpoint right there at line 72 so that I can just kind of inspect the state of the register. So I'm going to say break at main.asm line 72. And then just to be sure I did that correctly, I'm going to say info breakpoints, or just a B is fine. And it's like, looks like I set it up correctly. Then I can type run to see what's up. Notice how it starts to run and immediately stops at that breakpoint. You can tell it stops there because it's at line 72. Then I'm just going to do info registers, or info R, just to print out all my registers. And we should see a confirmation of what we were hoping to do. So if I kind of like, maybe I'll pin this to the top for a second, always on top, how about that? So first we moved an immediate into R10. So notice how 12876 is in R10 right there. And then on line 53, we basically copied R10 into R11. So that means in R11, we see the same value. And then we'll move a quad word from the long integer. We'll dereference that pointer, stick it in R12. So if you look at R12, it's like this gigantic number. If I scroll all the way up, it's the same number here as in our source code. So that seemed to work. And then we're going to move the D word next, I guess, into R13. So that's this number right here. So that seemed to have worked. It's this number right here, the D word. And I'm going to get lost so fast scrolling up and down like this. Now we're going to move a word into R14. So R14 has 62111. And there it is right there. And then R15 is just going to take a byte. And it's going to take a byte. Oh, now I'm hungry. Now I'm hungry. That activated it. It's only been like, I think 4 or 5 hours since I ate. I guess that is usually when I need to eat again. Even though I gorge and fall asleep on the floor because I eat way too much every single time. Don't do that at home. R15 anyway holds the correct value. It's 222. I just want to show you overflow real fast. If we look at R14, we're using the word version. So it's only going to read, 2 bytes from that memory location. And it's only going to consider, 16 bits as being valid in that register. So if I use a number that's too big, it'll overflow. 2 bytes, the maximum number I can represent is about 65535, or from 0 to that number, or 65536 combinations. So if I just stick a 9 in front of that right now, that should overflow the system. So let me try it one more time. I'm going to do Q, because that was the last thing we needed to look at. And then I'm going to do make. Oh gosh, what's happening here? Okay, how about I do clear and make build, which is in my Makefile, and gdb main, so I don't have to type all this stuff out again every single time. What did I just do? Oh, nice. Okay, you know what? I swear, it didn't used to do this before. It's giving me a nice warning saying that value does not fit in a 16-bit field. I guess if I turned warnings off, which I don't want to do, then the program would run and it would overflow. Do you want to turn it off? Let's turn off warnings. Okay, just to show you. So here's my Makefile. Don't pay too much attention to it. Where the heck are the warnings? Where's the assembler running? There it is. YASM flags, and that's my variable up there. There we go. Okay, so I'm just going to make a copy of this line, comment out the original, and then I'm going to take out the command that says, or the flag that says convert warnings into errors. Your compiler is your friend. It was stopping me from doing something naughty, and now it's not. So I am now going to do a breakpoint at 72. So break at main.asm line 72, and then run, and then it breaks, and then I go info registers. Then if I look at, what was I just talking about? R14, was that it? Notice how 44607 for the word, that's a totally different value, right? So this is what happens when you overflow or underflow. You got to be careful about your data sizes. I'm just going to do this again one more time just to make sure that it's fixed now that I moved it. And I'm gonna re-add that part about warnings, because I love converting warnings to errors as just a way to help myself write better code. Okay, so let's do that. And you know what I'm going to do too? I added another target here. Again, this is not a YASM, or sorry, this is kind of a YASM video. This is not a GDB video, but I do have a little extra file called gdb.txt where I can stick GDB commands. And so I don't want to continue to type my breakpoints over and over again every single time. So I know for sure I'm not going to change the program anymore. At least I'm not going to shift the lines up and down before 72. So I'm going to do breakpoint. You can type like break, or I think you can type either break or the full word breakpoint, but I just type B. Name of the source code file, a.asm at line 72. And so this file right here, again, this is not a GDB tutorial, but in my Makefile, I have it set up so that GDB will execute whatever commands I put into this text file. So it just kind of saves me typing. So let's put a breakpoint there, and then we'll say info breakpoints, and then we'll just run the program in that way. I can have a little bit more information So I'm going to do make build instead of make build and then running GDB. I'm going to say make debug. That's another target in my Makefile. So then you can see it added the breakpoint for me, and then it immediately broke on that. And you know what? Yeah, I guess I'll just leave it in where I have to type info registers. Okay, so we're just making sure I think that R14 is still a valid value and that it was fixed. Okay, so we've gotten this far. The next thing we need to do is prove that data size matters by specifying a bad data size for our long and then for our byte. So I'm going to copy paste a little proof here that is followed by another non-operation. So I'm going to do this. And so I'm going to try to prove to you that the data size matters by specifying a bad data size. I just proved to you that it kind of mattered, or it definitely mattered in terms of overflow and underflow, but I'm trying to prove to you now that it matters when you're reading. So I'm going to clear out R12, and then I'm going to move a byte from the long integer into R12B. And you know, this would be a warning, or I think this wouldn't compile or wouldn't assemble if I didn't have the B there. So I'm basically telling the computer, all right, I want you to use only a byte of R12, and I want you to take 1 byte from memory and just put it in there, but I'm taking it from memory that belongs to a quad word. So I should get something that looks awful. And then right after that, I'm going to do another naughty thing. I'm going to move something into R15, and I'm going to move a qword of memory into R15, but I'm going to be taking it from the bytes memory. So remember, a byte is just 1 byte, and so the next 7 bytes that come after it definitely have nothing to do with that byte, but I'm going to interpret them all as a quad word. So we should get nonsense data in both R12 and also R15. I don't really need to zero out R15 because the fact that I'm specifying R15 means I want to use all 64 bits. So it is going to definitely zero it out. And whatever we see in R15 is going to be the real thing. But in terms of R12B, we're only going to be loading up 1 byte's worth of that register. So that's why I'm zeroing out the rest of it, just to prove to you that we are truly getting nonsense. So now there's going to be another breakpoint at 82. So I'm not going to break anymore at 72. I'm going to break at 82. So let's do that. What's going on here? We got that. Oh gosh, okay, quit. I guess that means I need to comment this out. Let me do that. We'll do break at main.asm at 82. And you could do both of these to actually, let me do it first. We could do multiple breakpoints. Yeah, I'll just do it first, just to show you one time. So notice how it first breaks at the 72, and then I do C to continue, and then suddenly it breaks at the 82. But I don't want to have to hit continue a bunch of times, so I'm going to comment that out for the future. Let me quit real fast to make sure I remember what GDB expects as a comment. Yeah, okay, 82. Okay, so then I'm going to print the registers, info registers, and we're looking at R12 and R15. You can see R12 has the number 144, which definitely doesn't make sense because there's no 144 anywhere in our original data. So hopefully that's proof to you that we've grabbed some junk. Sometimes maybe when you're doing this at home, if you're just going to grab 1 byte, maybe accidentally, no, that would definitely still look bad. But for the R15, if you're going to grab a qword's worth of data, I don't know, maybe the junk data is like accidentally correct in a way where it would still make it look like the intended value. No, it wouldn't. There's no way that would even happen. No, I guess the junk data could work that way. Anyway, so we'll look at R15, 28 and a bunch of 4s and then a 238. That value does not exist up here. So again, junk data mixed in with real data is bad news. Okay, so now let's do another proof. I want to prove to you that symbols are pointers, you know, like I've been saying, and they need to be dereferenced. So let's first start off by moving the raw pointer from my long int into R10, and then into R11, we will dereference that pointer. So in R10, we should see something that looks like a memory location, or at least a relative memory location, and then in R11, we should see the actual long integer like we saw before. And then I'm going to mess around with some arrays. So remember up here we made an array. Let me minimize that real fast. We made an array, a very small array. I just specified a bunch of 1s and then specified a bunch of 2s. So it should be contiguous memory since it's been allocated as an array with that comma there. We should see, if we looked inside of the system, inside of memory, we should see 8 bytes representing the 1s. And then right next to that, we should see 8 bytes representing the 2s. And this will make it easy for us to sort of move our pointer around a little bit. So what else do I need to copy paste here? We got that long int. Okay. So I'm going to grab the first item and the second item in those arrays just using some pointer manipulation. So you know how to do this already. You just take like the pointer to some number and you just dereference it and you end up getting a number. If this feels a little weird to you, I understand your feeling because you might be thinking, wait a minute. I understood it when it was dereferencing just one number. But didn't you say this is an array? Why is it we can dereference the array and just get one number still? Well, remember, a pointer to an array is really a pointer to the first item in the array. That's kind of how it works. So either way, whether you consider that to be, a pointer to one number or a pointer to array, when we dereference it, we'll get one number. If you want to get the other numbers, then you have to start manipulating the pointer or dereferencing in different ways. So here's how we can get the second item. We deref the original pointer plus 8. 8 because it's a quad word. So, it probably would be a little smarter to put that 8 up into a define somewhere so you're not hard coding numbers, but I'm not going to do it. So basically in R12 we should see the 1s, in R13 we should see the 2s. And then a couple more things. Next, we will grab a pointer to the first item in the small array. And we'll just stick that into R14. So, we kind of did that with R10 already, but now I just want a pointer to the small array, and I'm going to keep it in R14 just so you can see the memory location. And then after that, we're going to grab an actual pointer to the second item. So remember before we talked about, hey, how do you get a pointer to the second item? Well, it's that. But then what if you didn't want to dereference the pointer? Like what if R13, here clearly because we have these brackets for dereferencing, you're allowed to put the formulas inside of the brackets. What if I wanted to get the address to the second item and not actually the second item? We would not be allowed to remove the brackets. The assembler wouldn't like that. So without another instruction, there's no way to actually get a pointer with a complicated mathematical formula. You can do like multiplication inside of here and other things in parentheses. So we wouldn't be able to do that without the other instruction that I'm introducing now called LEA. LEA just means, yeah, sure, we're still going to use the brackets to figure out where the pointer is, like figure out what memory location we want with some sort of a formula. But then what will be stored in the first operand is still the actual pointer. So this LEA won't dereference just because there are brackets. LEA will keep the pointer. And then finally, once we actually have a pointer to the second item in R15, then we can move the second item into another register. And this is like an LOL because I ran out of registers already. So I'm just going to use RDI, which is usually the first argument. It doesn't matter, it's fine. So if we dereference R15, it's the same thing as dereferencing this. We could have also just dereferenced R14 and it would have been the same thing as just getting the value of the first item. But I hope you can see now that, that expression is going to be a pointer to the second item in the array, and that's going to be stuck into R15. So if we dereference that, we can treat R15 like a pointer. It's just, it's a general purpose register. It doesn't only need to hold integer values. It can also hold pointers because pointers are integers. They're just unsigned. So we deref the pointer that is stored inside of R15 now, put it inside of RDI, and then we should see that RDI actually holds the second item, which should be a bunch of 2s. So the last thing that I'm going to copy paste in here is another nope. So I'm going to break at 108 just so we can see the rest of it. So I'm going to open up this right here and I'm going to comment that out and I'm going to say break at 108. Whoops. Okay, there we go. Quitsies. Now I'm just going to run make debug again so that I can enter GDB. And we've hit our breakpoint. So now I'm going to go info registers and just talk about the stuff that we're seeing. Okay, so the first thing, I think this is all on one page, right? I don't need to scroll. Yeah, okay, this is all on one page. First thing we see is R10 holds this value right here. That's a pointer to the mylong int. That kind of looks like a pointer if you consider that it could be relative. And then R11 holds the actual integer. And if you recall, that is the gigantic long that we put in there. Great, so now that's the difference between a pointer and its value, or in its dereferenced value. So then we're going to grab the first item in the small array. So R12 should have the ones. If we look at R12 here, it's got the ones. Again, just trying to prove to you that if you dereference a pointer to an array, you're actually dereferencing a pointer to the first item. And then on R13, we're going to make a pointer to the second item. Then with the brackets and the move instruction, we dereference that, and that should become the 2. So if we look at R13, notice how it's the 2s. Then we're going to grab a pointer to the first item in the small array. Hang on a second. What did I want to say about that? In the small array to R14. Okay. So again, we're just going to grab an actual pointer to the small array. And so the difference between R12 and R14 is the derefed value or the pointer. So if we look at R12, that's the actual value that we're pointing at. And then R14 is the memory location that we have in there. And then notice how it's kind of similar. Maybe this proves a little bit more that these are pointers that we're looking at. R10 was supposed to be a pointer, and now R14 is also a pointer. Notice how those numbers are pretty close together. I'm sure if we looked back up in the data section and we calculated an offset based on how big each data item was, we could probably predict what the memory location of R14 should have been based on R10, because you can see it's like only increased by a little bit, right? It was like 534 to 49. What is that? 10 plus 5, so that's like 15. Is that correct? Oh, I guess I had a byte in there, so maybe that's why it's kind of odd. But yeah, we can just compute the offset. And then we'll grab a pointer to the second item using the LEA instruction. Remember, we have to use brackets if we're going to do an expression, but then the brackets are dereferencing in the move instruction, so we just use LEA to not dereference. So we should see that R15 is about 8 bytes further along in RAM than R14, because both of those items are contiguous in memory and they should only be about, a quad word apart, 8 bytes. So if we look at R14, it's got this number, so it's a pointer. And then if we look at R15, what's 49 plus 8? It's 57. So you can see that the pointer to the second item is only 8 bytes further in memory. Yay, contiguousness. And then, sorry, I can't resist. So then finally, we'll look at the dereferenced R15, because it's now a pointer. What was it? It was a pointer to the second item. That should be a bunch of 2s, right? Because remember, in our array, we had a bunch of 2s here as our second item. So when we look at RDI, it should have a bunch of 2s inside of it. So if I look at RDI, where the heck is that? Right there. Has a bunch of 2s inside of it. RDI, baby. Oh my gosh, why did I say that? Anyway, so that's our non-operation instruction. And I think that's everything that I wanted to talk to you about in this video. So now I hope you feel like you're an expert in moving integers and moving pointers and dereferencing pointers and manipulating pointers so you can get a pointer to something else and dereferencing those pointers or not whenever you choose. Thank you so much for watching this video. I hope you learned a little bit of stuff and you had a little bit of fun. I'll see you in the next video. Limit out. I'll never say that again. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community, so we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.